Welcome to the Twin Labs podcast, where we help you make better decisions using digital twins. All right, let's dive in. Today, we're tackling a concept that, well, it seems to be everywhere, doesn't it? Digital twins.
It really does. It's moving fast from just a buzzword to a genuinely essential tool, especially for industries dealing with, really complex stuff.
Exactly. You hear the term constantly, but I think getting beyond that surface level, really understanding what it is, how it actually works, and I guess why it matters so much now, that takes a bit more unpacking.
Absolutely. It's not just one single thing, is it? It's more like a convergence. You've got data, sophisticated models, analysis, all coming together.
So for this deep dive, we've pulled together quite a bit of source material, right?
Yeah.
Expert views, history, real-world examples.
That's right. We've got a really solid collection, definitions, background, applications. Think of this as kind of a guided tour through all that information. The goal is to help you build a really clear picture.
Okay. And just glancing through the sources, a couple of things jumped out at me straight away. First, the history about. Some of these ideas go back way further than you might think.
That's true. The core concepts have been around in some form.
And second, just the sheer range of uses. I mean, you see it in massive things like power plants, entire cities even. But then also down to tiny components and even healthcare. That surprised me.
Yeah, that versatility is definitely one of its biggest strengths. It's much broader than people often assume.
So what's the plan for this deep dive? What can you, the listener, expect?
Well, our aim is pretty straightforward, to give you that clear, structured understanding. By the time we're done, you should have a really firm handle on the core definition. You'll appreciate maybe some of that surprising history.
Okay.
You'll be able to tell the difference between the various types of digital twins, understand the actual benefits they bring.
Right, the practical value.
Exactly. And see where they're being used today across all sorts of sectors, and also get a feel for the, frankly, transformative potential they still hold. We'll break it down chapter by chapter, covering the basics, the types, the history, benefits, applications, and where it's all heading.
Sounds like a good roadmap. Let's get started then. Definitions first.
Agreed. Let's nail down the fundamentals.
Okay, chapter 1. What is a digital twin? At its core, what are we talking about based on the source material?
So the basic definition you'll always hear is it's a virtual representation of a physical object or system. Simple enough, right?
Seems straightforward.
But there's a lot packed into that. It's not just any virtual copy. The sources really stress some key features. First, it has to reflect the physical thing accurately. High-fidelity mirroring of its form, its function, how it behaves.
Okay, so accuracy is critical.
Absolutely. Second, it covers the object's entire life cycle. From the very beginning, the design phase, to manufacturing, how it operates, maintenance, and even, what happens at the very end of life.
The whole journey.
The whole journey. And crucially, maybe the most important bit, it's constantly updated from real-time data. That data is streamed directly from the physical thing it represents.
Ah, so it's not static, it's living, changing.
Exactly. It's dynamic. And finally, it uses sophisticated tools, things like simulation, machine learning, maybe reasoning engines, to help make decisions about that physical object,
Yeah.
to generate insights.
Okay, so it's much more than just a 3D model or a blueprint. It's this active, evolving digital counterpart. How does that connection, that real-time update, actually work in practice? The source mentioned a wind turbine example.
Yeah, the wind turbine example is perfect for visualizing this. So picture a real wind turbine out there spinning.
Right.
To create its twin, you first load up the physical turbine with sensors, lots of them. On the blades, the gearbox, the generator measuring temperature, output, vibration, stresses, plus environmental stuff like wind speed, direction.
So it's constantly monitoring itself and its surroundings.
Precisely. It's broadcasting its status, its performance, its environment, all in real time. These sensors generate this continuous flood of data.
Okay, a flood of data. Where does it go?
It flows into a processing system. You can think of this as the brain. It
Yeah.
takes in all that raw data, cleans it up, processes it, analyzes it, and then this is key. It actively applies that processed data to update the digital copy, the virtual model of the turbine.
So the digital model isn't just based on the original design specs. It reflects what the real turbine is doing right now.
Exactly that. It's a mirror of the present state, constantly being refreshed.
Okay, that makes sense. So now you have this incredibly detailed, up-to-the-minute digital model. What do you do with it? Where's the payoff?
That's where the real value comes in. Once you have this data-rich, living digital model, it becomes this incredibly powerful platform for analysis and decision-making. You can run all sorts of simulations on it.
But simulations based on its current real-world state, not just theoretical scenarios?
Exactly. You can test what-if scenarios based on actual current conditions.
Hmm.
Like, what happens if the wind picks up suddenly? How would a specific adjustment affect performance right now? You can test potential changes, predict when performance might degrade, model extreme events all virtually, with zero risk to the actual turbine.
Okay, so testing and prediction. What else?
You can really dig into performance problems. If something's not quite right, you use all that historical and real-time data packed into the twin to diagnose the root cause, much faster and more accurately than just looking at the physical asset alone.
Makes sense.
And, maybe most importantly, you can use it to design and test potential enhancements or optimizations. You model a change on the digital twin first, see how it performs virtually, and then decide if you want to implement it on the real thing.
So the main goal isn't just to have this cool virtual model sitting there. It's about actively using it to find insights that directly improve the original physical turbine.
100%. The whole point is to extract valuable knowledge from the twin. Insights about predicting failures, optimizing how it runs, making it last longer, whatever improves the physical asset. That knowledge then feeds back into actions, scheduling maintenance before something breaks, tweaking settings, planning design upgrades. It's all very practical, very action-oriented.
Okay. Now here's something the sources really seem to emphasize, and I think it's super important for understanding this properly. The difference between a digital twin and a standard simulation. They sound similar, but they're really not the same thing, are they?
Not at all. And this is probably one of the biggest points of confusion. It's crucial to get this distinction clear. Both involve digital models, yes, but they differ hugely in scope and function.
How so?
Well, the sources explain that a typical simulation usually studies just one specific process or scenario. Think about modeling airflow over just one wing design, or calculating stress on one specific part under one specific load. It's very focused.
Right, narrow scope, often
Yeah.
using fixed input data for that specific run.
Exactly. A digital twin, though, is described more like a virtual environment. It's a much richer, more complete representation of the whole physical thing, the turbine, the car, the factory, within its operating context. It holds data and models for all the relevant parts and how they interact.
So it's the whole ecosystem, not just one piece.
Precisely. And within that rich digital twin environment, you can run lots of different simulations, studying multiple processes and their interactions, either at the same time or one after another. It's like the difference between, say, studying one chemical reaction in a beaker versus studying the entire complex web of interactions in a rainforest ecosystem.
Okay, so the twin is the environment where you can run many simulations, not just a single simulation itself.
You got it. And the other massive difference, which we touched on, is that real-time data feed. Your standard simulation usually runs with static inputs, right? Predefined data for that specific scenario. It typically doesn't get that live, continuous stream of data from the physical world.
That real-time data is the lifeblood of the twin, then.
It absolutely is. It's arguably the defining feature. And tied to that is the direction of information flow. In a normal simulation, information mostly goes one way. You set it up, run it, get results out. End of story.
Right.
With a digital twin, the sources highlight this unique two-way flow. Sensors send data from the physical object to the digital twin. But then, and this is critical, the insights, the predictions, the recommendations generated by the twin get fed back to the physical object, or at least to the people operating it.
Ah, that feedback loop. So the twin influences the real thing.
Exactly. That feedback loop changes everything. It makes the twin part of an active, ongoing improvement cycle, not just a one-off analysis tool.
Okay, I see.
And it's this combination, the constant feedback, the richer, always current data covering everything, plus the advanced computing and analysis tools within that virtual environment. That's why digital twins offer so much more potential than standard simulations. You can study more things, see how they connect, predict outcomes from more angles, ultimately leading to much better improvements for the products and processes.
Okay, so just to recap Chapter 1 quickly. A digital twin is this dynamic, accurate, virtual copy that covers the whole life cycle, constantly fed by real-time data. It's way more than a simulation because it's an environment for multiple analyses and has that crucial two-way feedback loop, all aimed at improving its physical counterpart. That definitely clarifies the core concept.
I think that nails it. It gives us a solid foundation to build on.
Great. So, knowing what it is, let's broaden out a bit. Chapter 2 is about the different types of digital twins. The sources mention different levels like magnification.
That's a good way to put it. You can create a digital twin for things of vastly different scales, depending on what you need to analyze. And importantly, in any complex system, you'll often find multiple types of twins working together, kind of nested within each other.
So, what's the smallest level? The most zoomed in view?
According to the sources, the most basic level is the component twin, or sometimes called a parts twin. Think of component twins as representing the smallest individual functioning piece that you'd want to model, maybe a critical bolt, a specific sensor, a bearing, a valve.
Just one specific functional item.
Exactly. Parts twins are similar, maybe sometimes used for slightly less critical individual pieces, but essentially the same idea, the fundamental building blocks.
Okay. So, you have twins of individual components. What happens when you put components together?
Right. When you have two or more components working together to do a job, they form what we call an asset.
Mm-hmm.
So logically, the next level up is the asset twin. This represents that collection of components functioning as a unit.
Like an engine or maybe a pump.
Perfect examples.
Hmm.
An asset twin lets you study how those components interact within that unit. You're looking at the performance of the asset as a whole. The data you get from an asset twin, say, the overall efficiency of that engine or the vibration signature of the pump, can give you more complex insights about its health or potential problems than just looking at individual component data in isolation.
Okay, so components combine into assets. What's the next step up?
When you bring different assets together and they interact to form a larger, complete functioning system or maybe a major subsystem, that's where you get a system twin, sometimes called a unit twin.
So if the engine is an asset, maybe the entire car's powertrain is a system.
Exactly. Or think about an aircraft. The engines are assets, the landing gear is an asset, the flight control surfaces are assets. A system twin could represent the entire aircraft, showing how all these different assets work together during flight. It gives you visibility into those interactions between assets. Analyzing a system twin might reveal, for instance, that optimizing one asset negatively impacts another, or it could suggest performance improvements based on how the whole system functions together.
Got it. Components, assets, systems. Is there a level above that?
Yes, the widest view is the process twin. This is really the macro level. A process twin models how entire systems work together within a larger operation or facility. Think about a whole manufacturing plant, or a complex supply chain, or maybe even a city's traffic management system.
So not just one machine or vehicle, but the whole factory floor or the entire logistics network.
Precisely. Process twins focus on the synchronization, the flow, the dependencies between different systems. You're asking questions like, how does a delay in System A affect System B downstream? What's the optimal timing for the entire production line to maximize efficiency? How does energy flow through the entire power grid? They help you understand and optimize these really large-scale interconnected operations.
Wow, okay, so it scales all the way from a single bolt to an entire factory or grid. Component, asset, system, process, and you said these often coexist.
Yeah, absolutely. In a complex environment like a factory, you might have component twins for critical machine parts, asset twins for individual machines, system twins for production lines, and a process twin overseeing the entire plant floor. Data and insights can potentially flow between these levels, giving you both granular detail and a high-level overview.
That layered approach makes a lot of sense for tackling complexity at different scales. Now, moving on to Chapter 3, let's talk about the history. It feels so cutting edge, tied to AI and IoT, but you mentioned the ideas are older.
They really are. While today's digital twins rely heavily on modern tech, the sources point out the conceptual groundwork was laid quite a while ago. The first big articulation of the core idea, mirroring the real world dynamically in software, is often credited to David Gelernter's 1991 book, Mirror Worlds.
1991, wow, that's earlier than I thought. Just the concept, though.
Yeah, more the visionary idea. Applying it specifically to manufacturing and physical products came a bit later. The sources give credit to Dr. Michael Greaves, who, back in 2002, proposed this concept as part of product lifecycle management. He actually laid out what he called the digital twin software concept, explicitly linking the physical and virtual.
Okay, so Gelernter with the vision, Greaves applying it to manufacturing. But the name digital twin itself came even later.
That's right. According to our sources, the actual term digital twin that we use all the time now, that was apparently introduced and popularized by John Vickers at NASA around 2010. So you see this progression, abstract idea, then the industrial application framework, then the specific name catches on.
Interesting timeline. But the sources also mentioned something even earlier, right? About NASA using the principle long before any of this.
Ah, yes, this is probably the coolest bit of the history. The sources argue that the fundamental idea using a linked physical replica for real-time analysis and problem solving was actually pioneered by NASA decades earlier, during the Apollo missions in the 1960s.
The moon landings. How did they have digital twins then?
Well, they didn't have digital twins in the way we think of them with sensors and real-time data feeds. But what they did have for every single spacecraft they sent up was an identical, fully functional physical replica built right here on Earth.
An Earth-bound twin, like a stunt double for the spacecraft.
Kind of, but much more sophisticated. These weren't just mock-ups, they were high-fidelity working copies. And Mission Control used these Earthbound twins constantly. If something unexpected happened on the actual spacecraft millions of miles away, say, the famous Apollo 13 incident, the engineers on Earth would work frantically on the replica. They'd try to replicate the fault conditions, test potential fixes, simulate maneuvers on the twin before telling the astronauts what to do.
Wow. That's basically the core digital twin concept in action, just using physical hardware instead of software. An accurate replica used for study, simulation, and decision support for the remote asset.
Yeah, exactly. It perfectly illustrates the underlying need. Even without the advanced digital tech, in that incredibly complex, high-stakes environment, they understood the critical value of having a mirrored counterpart to understand and manage the real thing. The need was there long before the digital tools caught up.
That's a fantastic piece of history. Okay, so we know what they are, the types, and where the idea came from. Let's get into the real meat. Chapter 4, the advantages and benefits. Why are companies investing so much in this? What's the tangible payoff?
The sources point to several major benefits, all stemming from the core capabilities we've discussed. A big one is better R&D research and design.
How does it help there?
Well, because you can build this really accurate virtual prototype, run simulations, maybe feed it early test data. You get a huge amount of information about how a product is likely to perform before you even build a physical prototype, let alone start mass production.
So you can catch problems or find improvements much earlier in the design cycle.
Precisely. You get insights that let you make necessary refinements early on. Finding a design flaw in the virtual world is infinitely cheaper and faster than finding it after you've built expensive tooling or started manufacturing. It speeds up innovation and cuts down risks significantly.
Okay, that's a clear win for development. What about once the product is actually being made?
That leads straight into the next big benefit: greater efficiency in operations. Once you're manufacturing something, digital twins can mirror and monitor the entire production system, the machines, the assembly lines, the flow of materials.
Like the process twin we talked about.
Exactly. By analyzing the real-time data coming from the digital twin of the factory floor, operators can spot inefficiencies, predict when a machine might be about to fail, optimize the workflow. The goal is to reach and maintain peak efficiency across the whole process.
So it helps keep things running smoothly, minimizing costly downtime, and maximizing output.
That's the idea. Keep the machines running, keep the products flowing. And then there's a benefit that maybe isn't always top of mind, but the sources highlight it: managing product end of life.
End of life. How does a digital twin help when something's basically worn out?
Remember, the twin spans the entire life cycle. It accumulates data not just about performance, but also about the materials used, how components aged, how it was put together. So when a product, say, a complex machine or vehicle, reaches the end of its useful life, its digital twin holds valuable information.
Information about what, specifically?
Information that helps manufacturers make smarter decisions about final processing, things like recycling or remanufacturing. The twin can help figure out which components might still be usable, which materials can be effectively recovered, maybe even the best way to disassemble it. It supports that whole circular economy idea.
That really closes the loop, showing the value extends right to the very end. So better design, more efficient operation, and smarter end-of-life handling. That's quite comprehensive.
It covers the full spectrum.
Now, despite all these advantages, the sources are also clear. Digital twins aren't necessarily for everyone or everything. Chapter 5 talks about the market and industries, who benefits most, and when might it be overkill.
Yeah, that's a really important practical consideration. Implementing a full-scale digital twin is, let's be honest, a significant undertaking. It requires investment in sensors, data infrastructure, software expertise.
So it needs to be worth it. When might it not be?
The main factors seem to be complexity and criticality. If the physical object or system isn't very complex, its behavior is pretty simple and predictable, not many interacting parts or failure modes, then you might not need that intense constant stream of sensor data and complex analysis. Simpler monitoring might do the job.
Makes sense. And the cost.
Right. If it's a relatively simple object, or maybe the consequences of it failing or being inefficient aren't that severe, then the financial investment needed to create and maintain a super accurate real-time digital twin might just outweigh the potential benefits you'd get from it. The ROI needs to make sense.
So complexity and the cost of failure are key. Where do they make the most sense? What kinds of projects and industries are really leaning into this?
The sources identify several characteristics of projects that are prime candidates. First, physically large projects. Think big infrastructure buildings, bridges, tunnels. These involve complex engineering, huge costs, public safety. So detailed virtual modeling and monitoring is essential.
Okay, big structures. What else?
Mechanically complex projects is a huge area. Jet engines, cars, trains, aircraft, anything with thousands of intricate interacting parts. Improving efficiency, predicting failures in these complex machines offers massive value.
High complexity machinery. Got it.
Also power equipment. Generation facilities, turbines, nuclear reactors, and the transmission grids. Again, scale, criticality, complex physics make twins very valuable here. And, as we've discussed a lot, manufacturing projects, especially complex industrial settings with interconnected machines where optimizing the whole process flow is key.
Right, and those project types naturally point to specific industries leading the charge.
Exactly. The industries where you see the most successful and widespread adoption are ones like systems engineering, the automotive sector, aircraft manufacturing, rail transport, building construction, and facilities management, sometimes called the built environment.
Okay.
Also, general heavy manufacturing across the board, and power utilities. These are all sectors dealing with big investments, complex operations, and high stakes if things go wrong.
It seems like a clear pattern emerges, and the market data reflects this demand.
Oh, absolutely. The sources are very clear that the market for digital twin technology is expanding rapidly. It's not niche anymore. The demand is strong and growing. One source, back in 2022, even projected the global market could hit something like USD 73.5 billion by 2027.
73.5 billion, that's a serious number.
It really is. It shows just how significant this technology has become and how much growth is still expected. It's shifting towards being a standard requirement for many complex businesses.
That figure really drives home that this is a major technological and business shift happening right now.
No doubt about it.
So let's drill down a bit more into one of those key areas. Chapter 6 is specifically about improving manufacturing efficiency. We've touched on it, but how do twins deliver those efficiency gains in practice?
Right. Manufacturing is such a core application area. It's got the complex machines, the interconnected processes, the constant pressure for higher output and lower costs. It's almost the perfect environment for digital twins. The sources talk specifically about the impact of end-to-end digital twins here.
End-to-end, meaning covering the whole production line start to finish.
Exactly. It's about creating that connected digital replica of the entire process, from raw materials coming in through all the steps of machining, quality checks, right up to the finished product, and maybe even heading out the door. Having that complete real-time view gives manufacturers unprecedented insight.
And what are the main tangible results of having that insight?
According to the source material, two key outcomes really stand out. First, dramatically reducing equipment downtime.
How does it do that?
By constantly monitoring the health and performance of every single machine via its twin. The system can run predictive analytics to spot warning signs before a machine actually breaks down unexpectedly. So you can schedule maintenance proactively during planned downtime instead of having sudden, costly stoppages. Predictive maintenance, basically. Makes sense. What's the second outcome?
Upping overall production throughput. By analyzing how materials and workpieces flow through the virtual factory floor, the process twin, you can identify where the bottlenecks are. Where are things slowing down? You can simulate changes to smooth out the flow, optimize the sequence of operations, and basically fine-tune the entire system to produce more in the same amount of time.
So keep the machines running and make them run faster or smarter. That hits the bottom line directly.
Absolutely. It's about asset availability and overall equipment effectiveness. The source also gives a nod to this being implemented in the real world, mentioning a service lifecycle management solution created by IBM and Siemens as an example of these principles in action. It's good to know these aren't just theoretical benefits, but things being actively delivered by major industry players.
Definitely grounds the concept.
Okay, so manufacturing is a huge area, but let's widen the lens again for Chapter 7. Applications across the board. We've hinted at the breadth, but the sources list some really diverse examples.
Yeah, the range is quite striking. It really shows how adaptable the core idea is. Digital twins are being used extensively, well beyond just factories.
Let's walk through some of those examples. Power generation equipment seems like a natural fit, as we discussed.
It is. For those massive, complex engines and turbines, jet engines, locomotive engines, power plant turbines, twins are critical, especially, as we noted, for predicting maintenance needs. Analyzing all that real-time operational data lets operators establish really accurate timeframes for when maintenance is actually needed, rather than just relying on fixed schedules or waiting for failures.
Moving from scheduled or reactive to truly predictive maintenance. What about big structures? Buildings, bridges?
Huge area. Skyscrapers, offshore platforms, tunnels. Digital twins are used right from the design phase to model stresses, optimize the structure, even simulate things like wind load or seismic activity. But they also provide a living model for managing the structure over its entire life. And they're really useful for designing and managing the complex systems within those structures, like HVAC, electrical grids, plumbing, ensuring they all work together efficiently.
Okay. Manufacturing, we've covered thoroughly, noting how they guide products through the whole process.
Yes, fundamental there, ubiquitous across all stages.
But then there's the healthcare example. That one still fascinates me. How does that work again? Twinning a patient?
It sounds a bit sci-fi, but it's a logical extension. The sources explain that in this context, the physical object is the patient's physiological system. You create a digital twin using data from, well, all sorts of sources, maybe hospital monitors, electronic health records, lab results, even data from wearable sensors the patient uses.
So you build this dynamic, data-fed virtual model of the patient's current health status.
Exactly. This patient twin is continuously updated. And healthcare providers can use it to track health trends over time, maybe model how a disease might progress for that specific individual, simulate how they might respond to different drugs or treatments before administering them, and basically generate insights to personalize care and hopefully predict problems before they become serious.
Personalized and predictive medicine enabled by a patient-specific twin. That's powerful.
It really is. A very different application, but using the same core principles.
The automotive industry was another one mentioned?
Yes, very big in automotive. Cars are incredibly complex systems now, so twins are used heavily in design, modeling everything from engine performance to aerodynamics to crash safety, all virtually. And also in manufacturing, as we discussed, to optimize the production lines and assembly processes for efficiency.
And the last big example was urban planning. That's twinning on a massive scale.
Right, the city level. Civil engineers and urban planners are using twins to model entire urban environments. The sources talk about showing 3D and 4D spatial data. The 4D adds the dimension of time, so you can see how things change, like traffic flows, energy consumption patterns, maybe even air quality, all in real time or simulated over time.
Visualizing the living city.
Exactly. These urban twins can integrate data from traffic sensors, utility networks, environmental monitors, and the sources even mention integrating augmented reality. Imagine planners holding up a tablet in a real street and seeing digital twin data overlaid on the physical view, proposed building impacts, underground utilities, real-time traffic info.
Wow, so the applications truly run the gamut from tiny parts to individual people to entire cities. It really highlights the flexibility of the digital twin concept. If it's complex and generates data, you can probably twin it.
That seems to be the direction things are heading.
Which brings us neatly to Chapter 8, the future of digital twins. Given this trajectory, this expanding scope, where do the sources see this technology going?
Well, the sources paint a picture of, frankly, fundamental change. They talk about a digital reinvention happening across many industries, especially those with heavy physical assets. It's disruptive, forcing companies to adopt this integrated view, physical plus digital, for their assets, their equipment, their facilities, their processes.
And digital twins are central to enabling that integrated view.
Absolutely. They're seen as a vital part of this whole realignment. Looking ahead, the sources use pretty strong language. They say the future potential is nearly limitless.
Nearly limitless. That's a bold claim. What's driving that kind of potential?
The key driver mentioned is the sheer, relentless increase in cognitive power being applied to them. Think about the advances in AI, machine learning, advanced analytics, cloud computing. All these underlying technologies are constantly getting better, faster, smarter.
So the twins themselves are becoming more intelligent.
Exactly. It's not just about having the replica anymore. It's about that replica having increasingly sophisticated analytical capabilities baked in. They're constantly learning, developing new skills. They can handle more complex data, spot more subtle patterns, make more accurate predictions, generate more insightful recommendations.
So they evolve from just mirroring reality to actively understanding and predicting it on a deeper level.
That's the idea. As they get smarter, they can tackle increasingly complex problems, optimize systems with far greater precision, and generate insights that lead to better products and more efficient processes than we can even manage today. The sources also connect this to broader trends like Industry 4.0, the Internet of Things, even mentioning how generative AI might play a role in, say, creating or refining the digital models or helping interpret the outputs.
So the future is not just more twins, but smarter, more capable, more deeply integrated twins that become active partners in innovation and optimization.
That's certainly the vision presented. A future where they're not just passive representations, but active, intelligent agents driving improvement across the physical world.
Okay, we've covered a huge amount, the what, why, how, who, where, and the future. If you're listening and thinking, okay, this sounds powerful, maybe we need this, the obvious next question is, how do you actually get started? How do you implement this?
Right. Which leads us into Chapter 9. The kinds of services that specialized companies, like Twin Labs, for instance, offer to help businesses actually adopt and leverage this technology. Because it's not trivial to just switch it on.
What kind of help do businesses typically need?
Well, based on the sources, it starts right at the beginning. Remember we said twins aren't right for everything. So a key service is consulting and feasibility studies. Experts come in, look at your specific situation, your assets, your processes, your goals, and help you figure out if a digital twin is actually the right approach, what the potential ROI looks like, and what kind of twin might be needed.
So helping you make that crucial go-no-go decision and define the scope.
Exactly. Then, if you decide to proceed, there's the technical work. The sources mention developing agents. In the context of twins, agents usually mean the software components that do specific jobs, like collecting the sensor data, cleaning it, running the analytical models, maybe even triggering automated actions based on the twins' insights. Building these smart agents is crucial.
Okay, building the active parts of the system.
Right. And then there's the challenge of making sense of all the information the twin generates. That's where decision intelligence comes in. This is about taking the complex outputs from the models and translating them into clear, actionable insights that actual humans, operators, managers, engineers can understand and use to make better decisions. It's bridging the gap between the tech and the business outcome.
Turning data into decisions makes sense. And the predictive aspect.
That's covered by predictive modeling services. This involves using the digital twin platform to build and run those sophisticated models we talked about, predicting failures, forecasting performance, simulating different scenarios. It's about harnessing the twin's power to look into the future.
And finally, someone has to actually build the core twin itself, right?
Absolutely. That's custom digital twin development. Because every physical asset or process is unique, the digital twin needs to accurately reflect that specific thing. So you often need custom development work to design, build, configure, and integrate the twin solution so it perfectly matches the real-world counterpart and connects to the right data sources. Companies like Twin Labs offer these kinds of end-to-end services, helping businesses navigate the whole journey.
So organizations like Twin Labs provide that specialized expertise from the initial strategy and feasibility through building the custom models and agents to making sure the insights actually drive better decisions and predictions. They really help businesses unlock that potential we've been talking about.
That's precisely the value they bring. They make it achievable.
Okay, that clarifies how businesses can engage with this. We've covered so much ground. Let's wrap up with Chapter 10, a summary of the key takeaways. What are the absolute essential things you should remember from this deep dive?
I think the number one takeaway is that a digital twin is much, much more than just a digital model. It's a dynamic, living, data-driven virtual replica that's intimately connected to its physical counterpart.
Right, and that connection is key. The real-time, two-way data flow, combined with simulation, AI, machine learning, all used to generate insights and support decisions about the physical asset.
We learned they come in different scales. Component, asset, system, and process twins, allowing you to model everything from a single part to an entire operation. And these levels often work together.
And the benefits are real and span the whole life cycle. Better R&D up front, much greater efficiency during operation, and even smarter decisions at the end of a product's life.
And while they might be overkill for simple things, They're rapidly becoming indispensable in complex sectors like manufacturing, aerospace, automotive, energy, construction, and even branching into surprising areas like healthcare and urban planning.
And the future looks incredibly bright, driven by ever-increasing computational power, making these twins progressively smarter and more integral to how we manage the physical world. Twin Labs and similar companies are helping businesses harness this power right now.
I think the core lesson, if you boil it all down, is that digital twins represent a fundamental shift. They provide this intelligent, constantly updated virtual space where we can truly understand, analyze, and optimize complex physical systems in ways we couldn't before. They turn data into knowledge, and knowledge into action, across the entire life cycle.
It really feels like a technology that's moving from the cutting edge to being a core capability for navigating complexity. A powerful tool indeed.
Definitely, for a complex world.
So, as you think about everything we've discussed, here's a final thought. We talked about that accelerating integration of the physical and the digital, fueled by smarter digital twins. What happens when almost every significant physical asset, from infrastructure to products, has an intelligent digital counterpart constantly learning and optimizing? How might that fundamentally change not just industry, but maybe even our daily lives and interactions with the world around us? Something to ponder.
A fascinating question for the future.
Thank you for joining us today. Visit the Twin Labs website for more business insights.